Hello, class. This lecture is going to be on electric fields, nothing to do with vectors or line integrals or anything like that. This is going to be on electric fields and, of course, how electric fields influence charges, right? So let's just write that up here. Electric fields. So the first thing that I want to really talk about as far as electric fields go is that they have to be for something like a capacitor. Let's just talk about capacitors first. On a capacitor, I have two different plates, and they're separated by a dielectric. Two different conductive plates that are separated by a dielectric. And you're probably saying to yourself, sort of like clouds, right? Clouds, up in the sky, those are obviously conductive because they're water vapor. So of course they're conductive. And clouds on average are about at 19 million volts, right? When you're up there flying through a cloud, the tops of normal clouds are at about 19 million volts. And I'm saying, if even clouds that are even relatively close to the surface of the earth, sometimes fog lifting or whatever, and those have relatively high potentials and everything. So let's say that I had some clouds that were at about 1,000 feet, right? Now, by 1,000 feet, I mean approximately 300 meters. And we know we've got about 19 million volts up there, and we know we've got 0 volts down here on the ground, right? And so this, you'd say, God, if the atmosphere is a dielectric, then I've really got myself a capacitor here, don't I? That's right. We live inside a capacitor. So I don't have to say, hey, shrink yourself down so that you can envision yourself inside a capacitor, because you live inside a capacitor. So you don't have to envision it. You live there. Now, that's at 300 meters, right? Just like a capacitor, a little capacitor might only be a millimeter thick or a couple millimeters thick between the copper plates that are inside it, but it's the same thing, because we know that the relative permittivity of the atmosphere is 1.0004. I think I got enough O's in there. So the relative permittivity of the atmospheres is about that. But the breakdown strength, and this is what we want to talk about today. And of course, I'm sure that I'm hopeful that you already know this. I'm going to write this up here. Dielectric breakdown strength. Because that's the thing that's different, isn't it? It's different between magnetic materials. I can flux into a piece of steel. It's just going to saturate out at 2 Tesla, right? What happens if I just keep loading up voltage on one side of a capacitor? Does it just saturate out and it just won't go any higher? No. No, it doesn't. It doesn't do that, does it? It blows up. That's right. It blows up just like a lightning bolt goes across our dielectric called the atmosphere. In a capacitor, dielectric breakdown occurs when you have a sudden charge discharge between one of the plates and the other plate. Now, it's interesting that we live inside a capacitor, right? But it's not a solid capacitor. It's not a solid dielectric like it is inside a capacitor that we usually use. It's a gaseous dielectric, isn't it? Not only is it a gaseous dielectric, it's a gaseous conductor plate on one side. The other side is a solid conductor plate, but this is a gaseous conductor plate. Interesting little capacitor we live in, isn't it? Now, let's not stop there. If that is dielectric breakdown, when does that occur? Dielectric breakdown for air is at 3, wait a second, yeah, 3, that's a 3 times 10 to the 6 volts per meter, right? So when 19,000, or the normal, I say normal, that's not, you know, it obviously could have higher or less than that, but it's far below 900 million, isn't it? 900 million volts per meter, or excuse me, did I say volts per meter? Where is that again? Volts, because I've already multiplied the volts per meter times the 300 meters, haven't I? Right. So when the tops of these clouds go from 19 million, like they are in a nice sunny day, up to 900 million, which is what they are in a very stormy thunderstorm type of day, where we've got a lot of lightning that's occurred with the cumulus clouds very close to the Earth, so that we've got this type of disparity, and they're up to 900 million volts. Well, now, you know, you think about it, how much voltage, how much power is in a lightning bolt? And it's 100 times 10 to the 12 watts in one lightning bolt, right? In one lightning bolt. Now we know that power equals energy divided by time. So energy is power times time, right? Power times time. Well, what is the time? What is the time for a lightning strike? Just a second, I'll write it right down here. Time for a lightning strike is 30 microseconds. Well, 100 terawatts times 30 microseconds equals 3 billion. Oh, I better, yeah. Oh, how am I going to do this? I'm just going to cut that out. So you know it in your notes. Equals 3 billion joules, right? 3 billion joules is the energy content of a lightning strike. Just one lightning strike has 3 billion joules in it. And you're saying, oh, 3 billion joules. Wow, that sounds like a lot. Billion, you know. Of course, you've got to think about it in terms that we can understand, don't you? So let's think about this in terms that we can understand. 3 billion joules. Well, we know that 1 kilowatt hour equals 3,600,000 joules, right? I'm going to let you do that because a kilowatt hour, isn't there 1,000 watts in a kilowatt? Isn't there 3,600 seconds in an hour? So 3,600 times 1,000 gives me 3.6 million. 3.6 million joules in 1 kilowatt. Well, how many kilowatts then is in a lightning strike? How many kilowatt hours is in a lightning strike? Well, 3 times 10 to the 9 joules divided by 3.6 times 10 to the 6 joules per kilowatt hour equals 833.3 kilowatt hours. Oh, that's not so bad, but still, we don't really understand how much is that? How much is a kilowatt hour? Well, the normal house, that you live in, a family house, uses about 20 kilowatt hours per day. 20 kilowatt hours. So this is equal to about 41 days of electricity for one home in one lightning strike. Does everyone see how I did that? Right? I want to mention another thing about lightning strikes too. The temperature for a lightning strike is 10,000. This is really what gets people. I mean, don't get me wrong. I'm going to do two things here. 10,000 degrees Kelvin. Now, that's equal to about 2 times the temperature of the surface of the sun, right? So not a good thing. But is that exactly what kills you? Well, it's not a good thing. It's not a good thing. Let's say that. But the real thing that kills you, and this is, do you see how all of the I've done all of this? By the way, is this in a book anywhere? No, I'm just trying to explain to you that we live in a capacitor, so that as we get into capacitance and electric fields, obviously capacitors are using electric fields. You'll understand what it is that I'm looking at here and all of the individual characteristics of electric fields. Not only the dielectric breakdown strength, but let's face it, the permittivity of the material there, the relative permittivity times the absolute permittivity, when we're working with electric fields. We're going to do an example in just a second where I'm going to try to force you into thinking that you got to forget Coulomb's equation now. Now, the force that you're going to find is going to be the electric field, right? Which is, we're going to figure out what the force field, the electric force field is around a particular particle. And then once we figure out what that force field is around that particular particle, we're going to multiply it by any other particle that comes around that particle into its electric field. Like, let's say, an electron, right? So that's the force equation. Start to forget the idea that it's Q1 times Q2. That's just between two forces, between two charges. That's the force between two charges. Well, we're no longer just dealing with two charges, are we? Now we're dealing with plates of charge. Now you see what we've got here? It's a whole plate that's filled with charge. And this ground plane down here, it's a surface of charge. Do you see what I mean? We're not just dealing with point charges anymore. This is a very simple electric field. It's just a very planar type of electric field. I got 19 million volts here, or I've got 900 million volts here, and then I've got 300 meters, so I could just separate it all out, and I can draw. I could draw my electric field lines, like this. And well, what do you know? My equipotential lines are going to be perpendicular to them just like I drew before on that microstrip transmission line in an earlier, I think it was lecture 6. Now, let's get back to this. What does really do you in, though? P equals IV. So I equals P over V, right? Well, 100 times 10 to the 12 watts divided by 900 million volts is going to give me, wait, don't tell me. I've got it right here. I'm sure it's okay. 100. I just did this a second ago, and I'm gonna probably feel foolish that I did it again. And no, that can't be right. What did I do wrong? Here, just a second. Do 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 do. Yeah, there we go. Okay, I'm sorry about that. That is 100, 111,111. Of course, I could take it out forever. Amps. So when a lightning bolt hits you, you have 100,000 amps running through you, or basically, I should say over you, because it's mainly running over you. You're probably wet when you're being hit, it's going through you. But the point is, it's coming so fast that it goes right through you too. So yeah, not a good thing. And I just wanted to point that out to everybody because, that's just sort of an interesting aside to electric fields and why they can be so damaging to your health. Now, the next thing that I want to look at in terms of electric fields, and did I ever turn this on? God, I didn't. I didn't turn it on, did I? No, I didn't. So I have no idea how long I've really been going here. But the next thing that I want to talk about is I want to talk about an electron gun inside an old TV or cathode ray tube. You probably remember when you were young that they didn't have TVs that were hanging on the wall. They had big clunker TVs that were sitting in your house that had a huge cathode vacuum ray tube in it. And inside that cathode ray, you had 2 electron guns, one to accelerate the electrons and then another one to deflect the electrons toward the place on the back of that vacuum tube that was coated with phosphor. Right? Isn't that how we saw TV? We would fire electrons to a phosphor coating on the back of a cathode ray vacuum tube, and then when the electrons hit the stuff, it would phosphor for just an instant, and of course that's how we changed the phosphors to have them faster and faster, and that's how we got TV. So I think everybody knows how that works, but you may not know how the electron gun inside it works. Now, I'm going to, draw something here. I'm going to make this, let's see, I'll put it right here. There we go. Is that 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. And I'm going to go down here about 4 away, and I'm also going to draw this. Now, this is 10 centimeters, and it's 4 centimeters wide. I'll draw that down here. 4 centimeters wide. Okay. Now, I wanted to sort of leave a space there because I'm going to have an electron coming through there. And the electron that's coming through there is going to be going right straight down the middle. Right? Of course, it won't be as big as that electron that I've drawn, but it's going to be going right straight down the middle. And why did I draw it so large? Now, what's going to happen to that electron is once it enters here, and it's going to be going 90% the speed of light, it's going to have been accelerated up to 90% the speed of light. How's that doing? Is that good? Yeah, I think it's good. Okay, so, but what it's going to do is it's going to be deflected. So as it travels along here, because there's an electric field across here, this is going to be deflected, and of course it's going to be going up exponentially in here. And then once it gets to the end of the copper plates, the copper plate on top, which is going to be 40,000 volts, and the copper plate on bottom, which is 0 volts, it's going to be deflected, right? And then when it's deflected out here, because along here it's going to have a force on it, it's going to have the force due to the electric field that I've got here, right? I'm going to have electric field here. And then also the electron itself is a charged particle, so it's going to be deflected as it comes through here. Now, as it's traveling through here, because that force accelerates it in the positive direction, right? The electron, being a negative particle, is attracted toward the positive 40,000 volts. So now it's traveling here. But once it gets to the very end of this, from that point forward, it goes straight. Does everyone see that? It goes straight because it's not being accelerated in any direction anymore. There's no electric field that is doing it. So it comes along here, but then when it gets to the end, you know, it's turning up. Really, what it's doing in here is it's doing an an exponential. I've exaggerated it, of course, but it's going up like that. Once it gets to the end, it's just going to be linear, right? Because there's no force. And in here, F equals ma, so you know, its velocity is changing, its distance is changing, and we have equations for all of those. Let me just write down that the couple of the equations that we have. So the final distance in any individual perpendicular direction, the y, the x, the whatever, is going to be equal to the original plus the original velocity times time plus 1/2 acceleration in that direction times time squared, right? Everyone remembers that equation. And another equation would be the final velocity is going to be the original velocity plus the acceleration in that direction times time, right? And it could be either in the x or the y direction. Now, I did say that the original velocity of this is going to be 0.9 c. 0.9 the speed of light. What is 0.9 the speed of light? Well, 0.9 times 300 million meters per second squared means that the velocity of the electron, right, is going to be 270 times 10 to the 6 meters per second. I hope everybody, I hope I didn't have to multiply that out. I'm sure everybody got that. And so it's going that fast. Now it is going to be deflected, and it's going to be gaining that deflection in the y direction, right? Let's just sort of characterize this. Let's say that this is my x direction and this is my y direction so that you can see what we've got there. And so like I say, in the electric field here, should we draw some electric field lines? If I had another colored pen, I would, but I'll use this pen here. Let's see if this works. So my electric field lines are going in this direction, aren't they? Hey, that doesn't look too bad. I thought it would look a lot worse. But my electric field lines are going in this direction. I've got an electric field there. What is, you know, this is where being an engineer, you know, we don't just have to wave our hands and think we can make gold out of lead. We can actually do the math. We can do the math. It's like global warming. Don't get me started. I've got friends on Facebook. Please don't get me started. They're high school friends, and I love them. But, you know, we don't agree on global warming. I don't know. Maybe Michigan isn't going to warm up. Who knows? So let's get back to this. How long is it? Well, actually, why not, before we do any of that, why don't we find out what is the electric field strength, right? What's the electric field strength here? Well, we've got 4 centimeters and we've got 40,000 volts. So if I wanted to find the electric field strength, I could actually, I'll just make it a magnitude right now, because I think everybody can see that the electron, being a negatively charged particle, is going to be attracted to the positively charged surface, right? So I'm not too worried about that. I wish I'd put that timer on, but I think I'm still okay. So we've got 40,000 volts divided by 4 centimeters. Well, that's 0.404 meters, right? So that's 100, or I'm really going to multiply this by 100. So that would be 1 million. Well, not 100. You know what I mean. The 4 is, you know what I mean. 100 or 1 million volts per meter. Now, I say volts per meter, but volts per meter could be newtons per coulomb too, couldn't it? Let's never forget that. Why don't I write that up here? Volts per meter equals newtons per coulomb. I always think of electric fields as force fields for elementary particles. So like if I had a guy running after me that was made entirely of electrons, right? And then I just turned on any positive power source, he would just be sucked right up to that power source. I wouldn't even have to worry about him. That's some Hollywood movie somewhere in the future. Now, we've got 1 million volts per meter. Well, that tells us what the force is going to be on that electron. What's the force going? You know, if I wanted to put a thing in here, I could say that that's minus 1 million volts per meter in the J hat direction, right? Because look at the arrows. I've drawn my electric field in that direction, so that's the direction it's in. Now, the force on the electron. Well, we know that in fact, why don't we just actually do it with this? Because the force on the electron is just going to be the electric field times the charge on the electron. So minus 1.602 times 10 to the minus 19 coulombs, right? Times minus 1 million newtons per coulomb in the J direction. And what does that give us now? I've got 1 million here. I got a minus and a minus. So we know that our answer is going to be a positive, isn't it? So the positive is going to just take 6 off that. I'm hearing a sound. I think my house is going to blow up. So I get 1.602 times 10 to the minus 13. The coulombs, of course, cancel out, so that would be newtons. And so there you go. And now is that plus? Let's look at our thing here. Well, here's my plus y direction, isn't it? Because I've still got j. That's just a scalar. That's my vector. So it's still j hat. So it's in the plus y direction, and yes, I drew it correctly. It's going up in that direction. It's changing in that direction, isn't it? And we know what the force is on the electron. You know, how long, well, actually, before we do that, why don't I say, okay, well, the force on the electron, we know that force equals mass times acceleration, right? So the acceleration of the electron in the y direction, what's the acceleration of the electron in the y direction? We know what the force is. The force is 1.602 times 10 to the minus 13 newtons. We know what the mass of an electron is, 9.1 times 10 to the minus 31 kilograms. So we can see that the acceleration in the y direction is going to be 176.8 times 10 to the 15 meters per second squared. Pretty darn fast acceleration, is it? But you know, an electron can handle it. An electron can handle that type of acceleration, right? It's accelerating. You know, what would the acceleration be at the end of the time it gets through this electron gun channel? Right? Because it's always, you've got to remember, it's always still going. You know, it's accelerating as it goes through there, but predominantly its speed is that 270 million miles an hour that it's going through there. It's getting velocity in the other direction, but that's in the y direction. That's not really changing the velocity in the x direction at all. So how long does it take to actually make its way through the whole tunnel? Let's call it a tunnel. Okay, well, we know the distance. The distance is 10 centimeters, so the time that it's going to take to get through there is 0.01 meter, and I'm going 270 million meters per second, so it should take me 0.370 nanoseconds. Or we could say it was 370 picoseconds, right? That's a very short time to be in there. I wonder how much I get deflected as I'm going through there. What is my velocity in that direction by the time I get to the end of it? Well, we're going to be accelerating in the y direction, so my final velocity in the y direction at the end of my electron gun channel is going to be my acceleration, because in the original in that direction originally I was going straight through, and now the force is pushing me up so that I've got a velocity contingent in the y direction by the time I come out of the end of that electron gun channel. So my final velocity is just going to be my acceleration in the y direction, 176.8 times 10 to the 15 meters per second squared, right? Times the time that I'm in the tunnel, which is going to be 0.370 nanoseconds. And that tells me that my final velocity in the y direction is going to be 65 million meters per second. So when you think of my total velocity, if I was looking at my velocity vector, I would be going originally, my original velocity vector would be 270 times 10 to the 6 meters per second I hat, right? And then, well, I'll tell you what, of course we know that. I'll put the final one down. So the final one is 270 I hat plus 65 times 10 to the 6 meters per second J hat. And if I wanted to write that as a magnitude and an angle instead of this way, I could say that that was 277 times 10 to the 6 meters per second. And the angle that it would be at, I'll just try and draw it down here. I hope I get that on there. Maybe I didn't. The angle that it would be at would be 13.54, 13.54 degrees. And so what I'm saying here is that this angle at the end, right, is 13.54 degrees. Now, is that what this would be, right? If we actually took that here at the very end of its acceleration phase, where would that be, and where would that be in relation to that? I could do that, but I'm not going to. I'm going to let you guys fool around with that if you want to, and you can use the distance equation. I was going to do that. I think I'm running out of time here, so I'm just going to let this be. We've talked a lot about lightning and about electron guns, and you can certainly see where I'm going. Welcome to electromagnetic field theory. This is still just electrostatics, and this is just the baby electrostatics. Wait till we get going.